Okay, so hello and welcome to the RANSAC in 2020 tutorial at CVPR, which has been organized by Daniel Barat, who had the introduction short one, TJ Chin from Adelaide, me, Jiří Matas from Prague, Czech Technical University, René, Munich, Ondra and Mitra Mishkin also from the Czech Technical University. I'll start with a short tutorial outline. So the tutorial has 6 parts, and in the first part I'll be giving the outline of the tutorial, which is just now, and I'll talk about the taxonomy of robust model estimation problems. Most people think about robust estimation as a single instance problem. So for instance, finding a single fundamental matrix linking geometry of 2 views of rigid scenes, but if the scene is non-rigid, you might have multiple motions and multiple instances have to be found. I'll talk about the basics of the RANSAC algorithm, preparing the ground for the other speakers to tell you about the advanced and recent techniques, and I'll talk about the basics of half transform, which would be the basic standard method for obtaining multiple instances of some geometric primitives. After 45 minutes, you see the times in Paris and Beijing time, and the PDT is the Pacific in the US. So I guess you should be able to pick one time zone which is close to you to get the offset. After 45 minutes, Ondra will continue with RANSAC improvements that have been published, let's say, in the last 25 years, talking mainly about the USAC components. Then after a break, long session, and he'll talk about RANSAC advanced techniques, things like what do we do if we do not want to the user to have to provide the inlier outlier threshold, the scale of noise, and some sampling techniques that significantly speed up RANSAC. And in a second part of his talk, he will touch this multi-instance model fitting, which is like detection of multiple homographies, motions, and so on. Now, despite calling this presentation and the whole tutorial RANSAC 2020, in fact, only the first part is about RANSAC. We know that RANSAC is not the only method for estimating a robust, mainly geometry, if we talk about computer vision, but other quantities. And TJ will talk about theoretical limitations of RANSAC. So what is achievable, what is not, and he will present globally optimal methods like branch and bound based techniques and mathematical approaches, and he'll discuss the benefits of such techniques in terms of optimality guarantees and may be paid off by some time, undefined run times. In a 5th block, René Rachtel will talk about for robust estimation, and this has come to attention of the computer vision community in 2 different ways. Often RANSAC produces something like geometry, rotation, translation matrices, things which give good error functions, and in principle such methods are an excellent way of training, for instance, low-level detectors and descriptors that produce correspondences that the RANSAC derives geometry from, but RANSAC is not differentiable. So if we replace RANSAC approaches, we could improve the whole pipeline end to end. Now, from the other side, it turns out that if some deep method could give you a very good estimate of what is not and what is an outlier, expressed by some weight, you can obtain reliable results, maybe not sensitive to outliers, by iterated reweighted least squares. So there are 2 sides of this thing. Getting a differentiable RANSAC allows us to train end-to-end whole pipelines producing geometry, and on the other hand, we see that iterated reweighted least squares, when the weights, initial weights, are really high quality, might replace or be combined with RANSAC. How these techniques, the differentiable deep approaches, the mathematical programming approaches, and classical RANSAC, how they really compare on benchmarking, that will be presented in 7 or 8 hours by Dmitro Mishkin, who effectively worked on a novel benchmark which consists of 3 problems: homographies, fundamental and essential matrix estimation, and 3D point cloud registration. And he will answer questions like, should OpenCV RANSAC be used or avoided? Best performing methods of those presented. I will, spoiler, perhaps I would just say that maybe the story is not that RANSAC should be put aside. It's still holding well, and maybe the truth will be that somehow it can live very profitably with the deep methods. So that's the outline of the tutorial. Okay, as Daniel has already said, feel free to do the chat. We have, like other organizers, not only the speaker to attend to the chat, so it's very difficult for the speaker to also look at all the chat windows, but we do have someone else sitting there, and he will be questions, or possibly unmute his microphone and talk to me, or you might also try to unmute. Hopefully we'll have no Zoom bombers, or how these guys who have nothing better to do than invade Zoom meetings appear. So if they don't appear, you might be able to give your question directly. Fine. So that's the plan, that's the intro. And let's go to this taxonomy of geometric estimation problems. We are in computer vision. Most of the stuff is geometry or motion related, also segmentation related. So it doesn't have to, okay, but segmentation of planes and surfaces can also be called geometric. So most of the time we'll spend our interest in this robust single class, single instance fitting problem. And maybe on this slide, the most important thing is to understand what is the instance and what is the class. So in this example, in the top 3 examples, the class is the class of lines, which you want to estimate properties of and at the top you see an example of a single instance of that class without possibly noise. The second, which is the most common problem we'll be spending time on, you have points belonging to that single instance of the single class, points on one instance of a line. You could think about it, correspondences belonging to single rigid motion, where the constraint would be the fundamental matrix, the epipolar geometry, immersed in some outliers. And I think in computer vision, methods that believe that they can live without outlier handling will not become popular in practice. Then Daniel, I will do this basic introduction, but Daniel will mainly talk about single class multiple instances, and we'll only briefly touch this multiple class, multiple instance. So here the classes would be circles, circles of multiple size, it could be rectangles, but it could be something like planar motion and unrestricted motion, or motion. You can have multiple structures present in the image, both in 3D estimation and in geometric primitive detection. So just a list of examples that cover what we'll be talking about. The first are detection of geometric primitives, including perhaps one of the first, say, computer vision or image processing problem, detection of trajectories in chamber tracings, that's recordings, that's the one here on the top right. Detection of geometric primitives, maybe counting coins, counting objects of some fixed 2D type. Then the popular epipolar geometry estimation for rigid structure as a first starting point, maybe of reconstruction pipelines. Detection of multiple planes. Planes are ubiquitous. And then we can go to more complicated things like segmentation of multiple motions. And it doesn't have to be two view, it could be multiple view. So you can have a sequence of images that would be our data points, maybe the trajectories, tracklets would be the input, and our output would be coloring the trajectory image so that one motion is associated with the group of points of that rigid object undergoing that motion. And on the right, we have multiple, again, that's actually part of the homographies. Now, you can have 2D to 3D problems or 3D to 3D problems. So interpretation of LiDAR scans would be detect planar surfaces. Maybe you can match, and this is a common problem these days in autonomous driving, match LiDAR scans to what you see in imagery, or recognize 2D objects in the LiDAR scans. So there is a broad range of problems that, and applications that the techniques we'll be talking about are applicable to. So the standard problem we know about, which we use to explain the real basics of RANSAC and other techniques, is the line fitting problem. We all understand it. Here the data points are 2D. We can think about them as 2D vectors, and our problem is to find the line which in some sense best fits these points. Now, or find the line means establish parameters theta star with optimal property. Now, of course, defining what is best fits is itself an issue. So the classical formulation is this. Take such line that if we sum over all points that were input to the algorithm, the sum of residuals, which are usually squared distances, is minimized. The advantage of this formulation is that it's solved in closed form, and that's well known, and maybe these days it's a high school maths problem, but less known is what is the statistical underpinning of this, the justification of the method, and it can be seen as maximum likelihood method, assuming IID noise. So IID independent points, so the noise on each point is independent and it's identical. Now the problem with heteroscedastic noise is the one where you know the noise for each point, and if it's known, it just slightly complicates the definition, but it's more or less very similar problem. And the least squares is again justified by the assumption that the deviations, the residual, have a normal distribution. Now, this is a well-established method. It's about to hold. There could be arguments who developed it. These are eminent mathematicians, but that doesn't mean that it does not merit a closer look, and that they are open, or there are issues that people are often not aware of. The one that it's not robust, that's the one people are aware of. But if we look at this thing again, we could see that in vision, very often, residuals are not independent, despite being considered independent in the. So, for instance, if you have a rigid motion in a rigid scene, which is independent of the scene, the outliers of the rigid scene, let's say the two-view camera fundamental matrix, they will be, of course, structured because they all undergo the same motion, and that can be expressed. And Daniel will talk later about how to do that. It's also thinks that hidden assumption, at least most people look at it that way, that X is a noisy observation of X prime here, which is the nearest point on the instance manifold. So the nearest point, this is the distance to the nearest point on the manifold. If we look at the line problem, then it's justified, because if we think about a point on the line, which we did not observe, that would be a noise-free point, and X is the noisy point we observed, and we think that the X is X is a realization of a noise which is centered at Q with some standard deviation sigma into D, we can look at the, we can say, well, okay, we do not know which point Q the X originates from. So we can integrate over the line origin of this X. This is just marginalization of the unknown Q. And it will turn out that the probability of X is indeed distance to the line. So it's not that the least squares for a line are not requiring this idea that X is originating from the nearest point on the line. The marginalization of the normal will give us another normal, and it works fine. Now, if we look, however, even on a slightly more complicated example, where we are trying to fit a circle to data points, they break down. So maybe I do not want to dwell that long on this slide, but it's like, you can look at it at home, but it's more or less, it says that despite these 2 points, x2 and x1, have the same distance to the circle, and but their probability given the circle, the probability of their observation is not the same. The density at x2 is higher than at x1, and the maximum for, it's here on this side, the maximum probability of x given theta is not on the true circle. So the curvature of the circle creates these maybe paradoxical things which people are not that much aware of, and unless it's, in many cases it does not matter, so people ignore it, but it's good to know. Of course, the main reason why these squares are used only after you get rid of outliers is that as soon as you have inliers and these outliers are very friendly, they are sort of uniformly distributed, your least squares fit is bad. So the solution, the standard solution to with inliers comes both from vision and robust statistics. And the idea is to say, well, okay, the least squares, this is like loss function per point. The quadratic comes from the logarithm of the normal distribution from and we'll replace it with either truncated least squares or this 0, 1 loss function, with the main property that if you have a gross outlier, it will have constrained influence, like the influence will be just, say, some constant function. And this was proposed by Fischler and Bowles in the vision community, and Roussel, I probably pronounce it incorrectly, I already ask, unless we have some sort of Dutch or Belgian speaker here, I have no way to do it correctly. So he proposed least median squares, which is effectively the algorithm behind is the same as RANSAC. And least medians of squares says, well, we'll use RANSAC-like, well, actually, this truncated loss function, and we'll say we don't know the scale, but we'll assume that at least 50% of the points are not outliers, and then the median is a robust thing. But of course, this assumption of 50% of inliers is very often not true in vision. So we have to, and in RANSAC it has been used many times in such conditions. So this leaves us with the problem of how to set scale of the noise for RANSAC if we don't know it in our problem. Very often we do know it, so maybe I'm doing reconstruction and I'm doing this for hundreds of pairs of images, so I can inspect the data. But of course, knowing the scale is an important problem, and Daniel's talk will be devoted part of it to this problem. So the algorithm for finding the optimal solution, or with hope of the optimality, we'll talk about that later because that hope is can't be fulfilled with any guarantees, is that we take a random sample. By random here I mean uniformly a pair of points. I measure the set of data which are consistent with that set of points. And now I'm talking about this. If I go back, I'll be talking about the RANSAC cost function. So we are just counting the number of inliers, which can be seen as like 1 minus counting the outliers and maximizing the loss, minimizing the loss function here. So we take sample, get the distances, calculate the number of inliers, repeat until we get some large consensus set. That's why it's called random sampling and consensus. And there is a convenient result which shows when to stop. That does not require the number of inliers to be known a priori. That's very important. Now, the analysis which gives us this guarantee is saying something like that. So let's say there is an epsilon, the inlier ratio. We do not, and the probability of inlier sample is Q choose M and over N choose M, which is approximately epsilon to the M. Why this is not exactly epsilon to the M? Because when I'm sampling from the N points, I am not going to return the points, because why would I return the point for the random sampling? If I sample a point twice, I will have a degenerate sample. So this is slightly better than this epsilon to M. Now, where this formula which says if I sample K greater than log 1 minus eta over log 1 minus epsilon M samples, how does it come about? So epsilon M is the probability, okay, this is the probability that the whole sample is correct, all M points. Size of the sample is chosen as minimal. So I take the smallest number of points which determine one or small finite number of solutions. Now, this 1 minus M is the probability that the sample is wrong, and to the power of K, this would be wrong, K times in a row, and we can calculate this formula. It says actually that any model there could be which has higher inlier ratio than epsilon has a probability smaller than this eta of being missed. So if we have a solution with the inlier ratio Q over N, the probability of missing some better models is dropping with their quality. So if I have, so for instance, it's clear after the first try that the model which would have 100% inlier ratio is impossible. And this is the result, 1 over P is the average thing. So that looks nice, but it's only probabilistic. Now, if we summarize the algorithm, which I just expressed informally, as input, we require the set of points. We need to have the estimator that estimates the parameter of the structure given the. And this is easy for epipolar geometry. It's more difficult for essential matrix. It's even more difficult for two gradient distortion. It's even more complex. So there is a whole literature. There's a whole literature on this, how to estimate from minimal sample. Then we need to have the loss function, which could be this 0,1 classical RANSAC, which is the only one for which the probabilistic guarantee that we looked at holds, or it could be MLESAC with a truncated quadratic function. And the user will provide the confidence in the solution. That's usually not a problem. You can go for 99, 95, your choice. In a standard setting, the user has to provide an outlier threshold. That's the one which decides what is an inlier. That can be often a problem if you are running some software in unknown conditions. And then the output is the parameter optimizing the cost function. Like in a classical setup, which will turn out not to be fully general, as Daniel will explain, it seems that if you have theta star, it's very easy to get the inliers. because you just check whatever is inside the distance threshold when you substitute theta star in this formula. And if you have, on the other hand, if you have the inliers, you can do these squares. So having the inliers or the theta star is the same thing, but in some cases it's not. That will be a surprise perhaps. So here we go, like the algorithm looks extremely simple. Select a random sample, evaluate, check the quality, the consensus set, just remember the best so far and go until the condition is met. This is exactly what was on the previous slide. So just to have like after 25 minutes, some sort of an interesting side story. It turns out that RANSAC was used before these squares were formalized. I don't want to say it's older than these squares because these guys like Legendre and Gauss who get the credit, they actually formalized things which perhaps have been used for millennia in some settings. And there was a problem in 1975. People were arguing whether the Earth is a sphere or oblate or prolate. So is it like, what type of object is the Earth? And the guys knew that if it was a perfect sphere, you can look at Polaris to get the horizon and make a certain travel along the meridian, and you could see that depending on where you were, your results would differ. So if the Earth was, this is the oblate, you will see longer segments close to the pole and the other way around in the other case. So you could do some surveying, get the length traveled, get the angle for that length. And this guy was trying to find out what is the shape of Earth. Roger Bošković, and he's managed to get surveying data from various latitudes, from Quito in Ecuador, even north in Lapland. And he got this data because sine square was his measurement, so that was just observation part. The arc length traveled in miles was also the observation, and he didn't know how to fit least squares to this, so he tried to fit pairs of points, and then he decided that Lapland is a little bit off, and for the remaining ones, which he thought were okay, so he did the robust part. He averaged the models, and it turns out that averaging models is related to bagging and stabilization of random variables. So this will appear in the talk on RANSAC with 2 A's and MAXAC later on. And his result was not too bad, and he came to the correct conclusion. So now let's go back to RANSAC and look at the properties. So RANSAC is extremely popular. Just the original paper has 25,000 citation. If you look at all the papers citing RANSAC for different the improvements and modern versions, you are getting towards 100,000. It's used many applications. You do not need to know the percentage of inliers because you can't know that in many cases, and it gives some probabilistic guarantee. Now, okay, people in real life know that there are no real guarantees, and that proofs of optimality live in mathematics and not in the real world, but it's actually not so nice to say, okay, you have a 1%, 0.5% probability of failing. Actually, in practice, you have a lower percentage because the confidence you give is usually at the moment when you find the solution, it gets high, it gets above what you required. But that's another more advanced topic that maybe Ondra will cover. So the cons are that you need to know the sigma. You are assuming IID errors, which in case of structured outliers like 3-4 lines in the image is not the case. You don't have the optimal solution guaranteed, and it's low if the inlier ratio is low because you saw this epsilon to the power of m. So if you have a model which requires 10 or in the minimal sample, some of these more complicated geometries with radial distortion go towards that, then you need many samples even for let's say mediocre pollution with outliers. And then there are some other problems. for instance, that RANSAC takes several times longer than theoretically expected. And this is due to the fact that when you explain it, it sort of becomes obvious, but it took a long time, that not all inlier sample will lead to a good model estimate. So if you have which are very near each other, that will be poorly conditioned, and there are some more sophisticated arrangements which will lead to the. If you want to fit a plane into 3D data and your 3 lines are on a line, that's easy to comprehend, but for 2-view geometry there are some special cases which are not at all obvious and careful analysis has to be done. And it turns out that that if you look at this very simple RANSAC, everything has been revisited and improved. So the first thing that caught attention was the 0,1 was replaced by a truncated quadratic. Random sampling, it turns out that if you sample with using spatial coherence of data, you can get much faster, you can get a faster algorithm. And also very often, like in the terms of correspondence, when you calculate correspondences either by the classical methods or deep nets, you do have some quality of the correspondence. And so not all correspondences are created equal. And this can be very profitable, exploited. So you have much higher probability of outlier sample than if you do random selection. People have worked on this parameter estimation to sort of deal with degenerate configurations. It turns out that this function where you evaluate the quality of a parameter also doesn't have to use the sum of all residuals. Like if you have lots of points that you are fitting to, like registering 2 surfaces, it becomes obvious very early on that your theta is not a good one, and you can terminate early. You can do clever things, and Ondrachum will be talking about that. Daniel Barad will be saying, well, we do not even have to stick to a single sum here. We can use neighborhood structures and turn this evaluation into a labeling problem and use graph cut techniques to take into account non-interdependent point errors. We can do, and then here where the original algorithm only remembers the best model so far, one can do much more. If we say, well, this looks like the best model, maybe we can use techniques like local optimization to improve it. And that actually looks like extra work, but it could be even faster, because if you improve it, this termination has this J star here, and if this gets better, you terminate early. And often these modifications come almost at not that much computational cost. You see that almost everything can be modified in this engine. 100 years of combustion engine, still the same thing, but probably poor old Benz would not recognize a modern engine almost. Okay, maybe I'm underestimating, very clever guy. And the last thing that got sort of attention is the automatic selection of threshold. Why that was not in the first plan? Because maybe for many practical problems you can choose a threshold, but of course, if now computer vision algorithms get used broadly outside of the computer vision community without expertise, being robust to the threshold becomes an important property. So I will now briefly run through the half transform, just to say that the single class multiple instance. So multiple instance is that there are multiple structures, not just one structure. Okay, you can run RANSAC for multiple structures, and it has been proposed called sequential RANSAC, but RANSAC has the bad property that in this type of scenario where you are detecting, I don't know, 15 lines, all those lines are outliers for each of them. So the inlier ratio gets very, very low, very fast, and for multiple structures, RANSAC becomes inefficient. This will be covered by Daniel. Yet the first, probably still used, still very popular if you look at Google Scholar technique, which computer vision produced is the half transform, which is from '62, a patent, where the bubble size, and you can see some spirals and parabolas and lines. And so in some sense, multiple instances in computer vision were tackled before a single instance. And the idea of the half transform is to say, well, okay, we'll discretize the space. Theta will now not be recovered by sampling, but by discretization. And for every point, here we are in the line problem. So this point, well, 9 lives on many lines. We will enumerate them. And this is the space of all lines for all the lines. So here we don't care about the outlier in some sense, the outlier percentage. Okay, every outlier will still vote, but the problem is linear in the number of outliers. It doesn't have this problem that if you need multiple points to fix the minimal problem, outlier, if the inlier ratio gets low, you get into trouble. Now, you can see that this can be easily generalized to multiple hypotheses. So these are some images from a paper by Gehrig in '87, who was saying, okay, we will use, let's call it sequential half transform. So unlike sequential RANSAC, sequential half transform is actually quite efficient. You do the half transform, take the mode, which would be the longest line if we talk about line detection. We can remove its support. So you unvote with those votes belonging to the mode, and then you go again. So, and what I like about this paper, that it says that it's a new approach to object recognition. So we have really traveled a lot. I think if you saw these images in current paper, you would not see this as object recognition. But that's, so we have traveled a lot in 30 years. The problem with half transform, but one of them, okay, of course, the main one is that you cannot use it for primitives or problems where you need a high dimensional accumulator space because it will not fit. And the other problem is that for a set of 7 short lines, or how many, 2, 4, 6, 8, 10, you would like to have this type of response, but what you get is something like this vertical line, because that has larger support than the single, than the short line. And why we would never interpret the data the way half transform would, because we see that the problem is that adjacent pixels are assigned to different primitives, and that you are declaring neighboring pixels to some other pixels outliers not connected to the structure you just found. And that's a fundamental problem, which is the summation. And again, Daniel will talk about addressing this problem. So compared to RANSAC, the advantages of half transform is that it can easily generalize to multiple instance fitting ratio. And talking about RANSAC mainly, is that the geometric problems we want to address are high dimensional to a level that the accumulator space becomes impractical. You can have projection techniques like, okay, maybe if I try to look for to register 2 images with a similarity, which would be scale translation, that can be done. Maybe I want to do similarity with rotation for dimension, that becomes tricky. So first I sort the translation and then try to do the other 2, but then it becomes a very heuristic method which has no guarantees. Now, last, I will just introduce the multi-class, multi-instance problem. It will be covered by Daniel, and it has, it's like been neglected. Maybe it doesn't have that many applications. So you can see that if you have an image like that, you can see this as 2 instances, 2 classes. One, the class of lines, and the second, the curves or ellipses. Or you can use this as like every single radius would be a different class. And Daniel will show how this can be converted into optimization problem where RANSAC is used for initialization, and then techniques coming from labeling problems, and because it's an assignment problem, can be used to fairly efficiently solve these problems. Like if you see papers even at recent conferences on this topic, they operate on much more toy-like data than, for instance, 3D reconstruction. 3D reconstruction is so mature that you get data which are very similar to what you will get in practice in running systems. This one is still at the level that toy-like approaches are okay. There are some results, and maybe you can see here the somehow what you have to do here is maybe sample intelligently so that you don't rediscover the structure again and again, and there is some competitive nature in this, and the labeling, and it becomes a labeling problem. Same thing, multiple planes, essentially the same problem as before. This time we're looking for multiple homographies, and this is a good example when you see that if you are doing multiple plane detection, they are spatially coherent. You will not get points evenly distributed, and it's very important to use the spatial coherence of data in this type of methods to get good performance. So the conclusions, or maybe summary, it's more a summary. Fitting of models is an old problem. They are both robust single class, single instance, and single class multiple instance, and multiple class multiple instance are open related problems. Basic RANSAC and half transform are the classics for robust single instance and multiple instance problem, and they have been successfully applied in image processing and computer vision. Now comes the warning. State-of-the-art implementations differ substantially from the simple algorithmic course that I presented in this introduction, and that's why you should hold on to Ondras and Daniel's talk. There are alternatives, like iterated relativity squares, and their relative merit has to be assessed. So often in computer vision, we used to have sort of fashions. People think this is fashionable, this is new, let's go for it. Then it turns out that it's not better than the old stuff. So SIFT, detector and descriptor, which I myself reviewed at least 30-40 papers on improvement of SIFT. Maybe hundreds were published, and then with the exception of root SIFT, everything was more or less thrown in the dustbin, and people used the original algorithm because it was an extremely good trade-off between, say, speed, performance, and so on. And to know what works, that usually cannot be, unfortunately, assessed from first principles, and we need to do benchmarking, and Metro will tell you about that. So this concludes my talk. Thank you for listening. And we do have like 2 or 3 minutes for questions. But if there are no questions, that's fine in 3 or 4 minutes. So thank you for listening, and I'll stop sharing the screen, and I'll still be watching the chat window if there's a question.